So here we are talking about impulse, momentum, and conservation of momentum. Well, this should seem familiar. This is what we've been talking about lately. Impulse, which is just force times time, is equal to the change in momentum. A good example of this is when you hit a baseball with a baseball bat. You apply a force over a period of time. The baseball has an initial velocity, in this example to the left. You apply a force on it to the right, and then the velocity changes direction and sometimes even magnitude, and the baseball goes in the other direction, and that represents a change in momentum. So what brought us here? Well, it all started with kinematics, and then Newton's second law, force equals mass times acceleration, and now we changed Newton's second law around just a little bit and figured out that force times time is equal to the final momentum minus the initial momentum. So here are the topics that we're going to look at in Chapter 7. Impulse and momentum, conservation of momentum, and then two types of collisions, and center of mass. So we've already looked at impulse and momentum and learned that a force applied over time changes the momentum of an object. But now what we're going to look at is when two different objects collide. Collisions! So here we have two objects, M1 and M2, and I think later we're going to end up calling them objects A and objects B. Before they collide, they each have their own momentum. Object A is traveling this way, so its momentum is that way. Object B is traveling this way, so its momentum is that way. And then down here, A and B collide. And object A experiences an impulse because it's being struck by object B. So that impulse is the force that object B applies on object A, and it occurs over a certain period of time, and it changes the momentum of object A. Well, when that collision takes place, the same thing is happening to object B. Object B experiences a force from object A for a period of time, and it's important to note that Newton's third law tells us that it's the same amount of force. And because they're colliding with each other, it happens for the same period of time. So both object A and object B are experiencing the same magnitude of impulse. So because they're both experiencing the same impulse, there's a special relationship that occurs that we're going to look at now. And what happens is the momentum of object A before the collision plus the momentum of object B before the collision is equal to the momentum of object A after the collision plus the momentum of object B after the collision. So the best way to figure out how to solve collision problems is by looking at collisions. So the first kind of collision we're going to look at is known as an inelastic collision, otherwise known as a smash. So, is anyone interested in crime scene investigation? Well, here's where physics comes in. So, what we're learning about with collisions is that momentum is conserved. The total momentum before the collision is the same as the total momentum after the collision. Alright, so the best way to learn this is just by working through an example. Here we have an example where we have a 1,055 kilogram van stopped at a traffic light that's hit directly in the rear by a 715 kilogram car traveling with a velocity of 12.5 meters per second. Now the van and the car stick together and they slide into the intersection, and we want to find the velocity as they slide into the intersection. Because they stick together, this is what's known as an inelastic collision. That's what an inelastic collision is. It's when two things collide and they stick together. Alright, so the first thing we want to do is we want to take a look at what we have and how we can simplify our equation. So here we have a van that's stopped at a traffic light, so its initial momentum is 0. So we can ignore that in the left-hand side of our equation. And then we have our car, it weighs 715 kilograms and a velocity of 12.5 meters per second. And that is the only object that has momentum before the collision. So here we have the mass of the car times the velocity of the car on the left-hand side of the equation. And on the right-hand side of the equation, because the two cars, because the van and the car are sticking together, they both have the same final velocity. So we can combine those two terms into this equation. Alright, so now we just plug our numbers in. Here with the mass of the car and the initial velocity of the car, and set that equal to the combined mass of the car and the van times the final velocity. And then we just solve this equation for v, and we get v, let's make that a little thicker. We get v is equal to 5.05 meters per second. Alright, here's another inelastic collision problem, very similar to the last one. We have a 0.0025 kilogram bullet traveling at a speed of 425 meters per second, and it strikes a wooden block that has a mass of 0.215 kilograms, and it embeds itself into the block. What is the speed of the bullet block mass right after the bullet enters the wood? So here we have the initial momentum of the bullet. Here we have the initial momentum of the block, which is 0, because it's not moving, is equal to the combined momentum of the bullet block system times the... So I'd like you to pause the video now and solve this problem. Alright, good job. I'll check your answer tomorrow. And now we have one more problem for you on the next slide. Alright, here's another one for you. In a football game, a receiver is momentarily standing still, having just caught a pass. Before he can move, a tackler running at a velocity of 4.5 meters per second grabs him. The tackler holds on to the receiver, and the two move together with a velocity of 2.6 meters per second. The mass of the tackler is 115 kilograms. What is the mass of the receiver? You're going to use the same equation, you're just solving for a different variable. And I will check your answer to this one tomorrow as well.